We can analyze the rocket motion by conservation of momentum. So you can see we have a rocket of mass m moving with velocity v. So this is the external velocity, or we can say this is the ejecting spent fuel, which is at the exhaust speed. Okay, and when we talk about the momentum, so at time t, this is the momentum of the rocket before moving. At short time, when we talk uh, at this time, so the momentum will be this. Okay, so you can see when the rocket is moving, its velocity is increasing along the direction of x, or we can say that along the direction of motion. Okay, and these velocity will decrease, it's obvious. So these decreases shows by negative sign. Here you can see. So first we take the total momentum. The total momentum is the sum of rocket momentum and the fuel that is ejected. Okay, and this is total momentum shows with this at that time. Okay, so you can see this is the momentum of rocket, and this is the momentum of after ejecting. So here negative sign shows that after ejecting the mass decreases, rocket mass decreases. So this is the negative sign. Okay, so after evaluating, you can see multiply these m with v, and after that m with dv, you will get these. Same the case with this, you will get these equations. So the opposite terms will cancel out. That one and this. Okay, we are remaining with these terms. So you can see the small change in mass and velocity, which is approximate, which is equal less than 0. So you can see we have to neglect it. Okay, because this is very small change. We are remaining with these term, and after applying conservation of momentum, so conservation moment, this is the momentum before ejecting, and this is the momentum after ejecting. Okay, so you can see after putting values, these two term will cancel, this one and this. Okay, and after arranging and dividing the term, these terms with dt, we will get these terms. You very well know this is the first order derivative, and this is the differential form, and we can also write it down in the form of dot, which is a symbolic representation of the first derivative order. Okay, so here you can see these negative sign shows that is the rate at which the rocket engine is ejected mass. It's obvious, and the product is called thrust. So here you can see these value. These value is similar like the force, the Newton's second law. By using Newton's second law, which is equals to m F equals to ma. Okay, so this is the same. And when we talk that there is a negative mass, so there is obvious thrust, which is always positive. Okay, thrust is also a force which is similar like force with when we discussed in Newton's second law. So you can see after taking equation 1 again, and cancel dt with this dt, you are remaining with these. After arranging dv remains same, m will go toward other. Okay, you can see after arranging these terms, we are remaining with these terms. Dv equals to minus vex dm over m. Okay, Now we have to integrate. After applying integration, which is at limit, this is the initial velocity, okay, this is the initial mass, and we have to move these uh, rocket to this velocity to this one and this mass to this one, okay. uh, After integrating you will get these values. You very well known that how to integrate the values. It's simple. We are remaining with these terms. You can see the negative sign is there, and after removing this negative sign we have to reverse the terms, okay. So this is the initial mass and this is the mass of the rocket. Further, when we talk about the explanation, you can see where VO is the initial velocity, MO is the initial mass of the rocket. The results put a significant restriction on the maximum speed of the rocket. So this ratio must be larger when the fuel is burned, okay, and M is just the mass of the rocket plus payload. Even for example, when we talk that the original mass is 90% fuel, okay, so this ratio is only 10, and after taking log of these 10, so this is the ratio which is 10, okay, after taking the log you will get 2.5. so what does it mean? That this value, which is the difference between rocket velocity and after ejecting, so that can be that cannot be more than this 2.3 times external velocity to the external velocity, okay. This means that the rocket engineer tries to make Vx as big as possible, and also design multi-stage rockets which can jettison and have the heavy fuel tanks of the early stages to reduce total mass for later stages. So it's all. Thank you.